We'll proceed in Taylor series, and later we will see kind of one special case of Taylor series, that is maclaurin series. So Taylor series is a polynomial approximation of any function. Polynomial approximation of any function fx. What is it? What it is? So if I have an algebraic function fx like sin x. Sin x is an algebraic function where it is a function over independent component x. Algebra plus calculus. Algebra plus calculus. Independent component, dependent component. Typically, independent component can be many and dependent component is one. Like if I have a volume, if I have a cube, if I have a volume, then this cube is made up of a metal, and metal density at different point in the cube is different. Density means kg per meter cube. Density is different at different point in the cube. So density is dependent component. It's a function at any point x, y, z. There will be algebraic function at x, y, z that will, whatever the value comes, that is the density at that point. So if I say I have a cube and everywhere density of the metal is different, quickly, suddenly, immediately, anyone would ask, then what is the algebraic function of the density based upon the coordinates? Actually, he is trying to ask that if independent component is x, y, z, any point in the 3D, then what is the dependent component, that is density at that point? Okay, so algebraic function in calculus is nothing but a kind of a function which has set of independent component and dependent component. We are proceeding towards kind of thinking in a way that we think that independent component is only one. Like here, x, y, z is independent component. We can say x axis, y axis, and z axis is the independent component. But we can also say that independent component is only one, that is x, y, z cube. If I have independent component at x and y and I have z value as dependent component, I can say fxy or z value is dependent upon xy plane, not x axis or y, only one independent. So this move we are making, and if we come to a solid formula, then that will be immensely great. So that you have now chain rule as far as independence is concerned. You can derive, we are seeing Jacobian matrix. Jacobian matrix is also a move towards the single independent component. Jacobian matrix, if you see, it is also a move towards single independent component, directly or indirectly. But if someone cracks it solidly, solid blow, right? So if someone cracks it solidly, the independent component and dependent component where both are one, or at least independent component is always one, a line, a surface, a cube, or 4-dimensional or 5-dimensional, later through chain rule, he can break it into, at the end, it will come at x-axis, y-axis, z-axis, and this axis and that axis. As we break in the chain rule, it will be amazing. Someone can try it. Okay, so what is polynomial approximation of any function fx? If any function fx is sin x, can we describe, can we write sin x in terms of a polynomial function, that is 1 plus x plus x to the power 3 plus x to the power 5 plus whatever infinite. This is called Taylor's polynomial approximation extension, or Taylor's polynomial approximation of any function. Okay, Taylor's polynomial expansion, whatever you can think of. There is a function fx. There is a function fx. Fx is a black box. Inside fx, there are polynomial x to the power n, any combination. So inside fx black box, there are polynomial, there are trigonometry, sinusoidal, tangent, tan, and then there is exponential, there is logarithmic, and there is so many functions inside fx. So fx is hybrid model. I don't care fx. That is the elegance. I don't care fx, whatever fx is. If this is fx, can I have similar function gx? Gx is mirror of fx. Gx is mirror of fx. Fx, gx. Gx is mirror of fx. If that is true, then gx is only polynomial function, that is a constant, plus x into constant plus x square into constant plus x to the power 3 into constant plus x to the power 4 into constant plus dot 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 plus x to the power n into a constant. This is a pure polynomial function of degree n. This is gx. Fx is a black box where everything is there. Can I, considering fx as black box only, can I create a copy of fx as gx, where gx is only a polynomial function, x to the power 1, 2, 3, 4, x to the power 0 till x to the power n? Is it possible? So it's possible. We gave our proof. Our proof in the sense, if I have a consider fx as polynomial one, simplest case, because at the end fx and gx are not exactly same. It is called approximation. They are exactly same at a point when x is a. If x is a, there they are exactly the same. Otherwise, they may not be exactly the same. We will talk about where it is exactly the same and where there are errors. Mathematics is an area where you know that there is approximation. Then certainly you can apply your mind where it will not be approximation, or it will be minimal approximation. Toward minimization, anyone can work. So this is kind of mathematics. Anyway, now if I have a, consider what proof we gave. If I have a function x to the power 4, fx equal to x to the power 4, can I replicate fx as gx in terms of derivatives? So if I derive it 4 times, x to the power 4, if I derive it 4 times, then it becomes 4 into 3 into 2 into 1. That's it, 4 times. If I want to replicate fx into gx, then I can say d to the power 4 fx by dx to the power 4 into x to the power 4 divided by factorial of 4. This is exact copy. So from fx, if I ask for the fourth order derivative, whatever the fourth order derivative is, if I write fourth order derivative d to the power 4 fx divided by dx power 4, fourth derivative from fx inside gx, I am making gx equal to d to the power 4 fx by dx 4 and then x to the power 4 divided by factorial of 4. If I write like this, where information I fetched from fx is fourth order derivative, then this will be exact replica of fx. Gx is exact replica of fx. If it is x to the power 4, k into x to the power 4, k into x to the power 4. If I ask for fourth order derivative, then whatever comes, then k will be multiplied there. No problem. So d to the power 4 fx divided by dx to the power 4 will have k also. So this is what we want. So constant is not an issue. Now next thing is that d to the power 4 by dx to the power 4 is a scalar value, numeric value. Okay. So it is, so whenever I ask for the derivation, I say that it should be at point x equal to a. Okay, please calculate the derivative at point x equal to a. This is where I am interested in. If I am asking at the point x equal to a, if there is a function fx and it is drawn in xy plane at, this is x-axis and this is y-axis. This is x-axis and this is y-axis. At any point a, if there is a function fx at any point a, if there is a function fx, then height is fa. If x is a, then height is fa. Okay, at that point, if derivative is fx by dx, first order, then if it is x, then I'll replace x with a. So at any point a, it wants it. Now let's rephrase this fx at, it is passing any point a. If I'm asking any point x equal to a, then this function is passing, the line is passing at x equal to a. If that is the case, then fx changes into equation like k x minus a to the power 4. If a function is kx to the power 4, this proves that it is passing through origin because x minus 0 to the power 4. Okay, if it is passing through a point x equal to a, then it is now kx minus a to the power 4. K is outside. K outside in braces kx minus a to the power 4. So that is the scenario. If that is the case, then gx becomes d power 4 fx by dx to the power 4 x minus a to the power 4 x minus a to the power 4 divided by factorial of 4. Okay, because we are taking care when now d to the power 4 fx by dx to the power 4, this is the scalar value we received from this function, that is at x equal to a. Okay, now if I try first order derivative, means if fx equal to x, kx, fx equal to kx square, fx equal to kx to the power 3, k can change, I mean anything I can take as constant. If I try to make a copy, exact copy in gx, then separate gx would be something like d to the power 1 fx by dx at x equal to a, x minus a by factorial of 1, d to the power 2 fx by dx square at x equal to a, x minus a to the power 2 by factorial of 2. This is for separately. If I say it has combination of everything, here also we will add combination of everything. So if fx is full-fledged polynomial, then gx is also full-fledged polynomial. So gx now it is fx dfx by dx at x equal to a, x minus a divided by factorial of 1 plus d2fx by dx square at x equal to a, at x equal to a, x minus a whole square by factorial of 2 plus d to the power 3, d to the power 3 fx by dx cube x minus a to the power 3 by factorial of 3 plus, so fx, we have, if fx is full-fledged polynomial, then the copy replica of fx at gx, we also have full-fledged polynomial. But gx is created when we receive from fx the information that is first order, second order, third order and nth order derivatives. That's it wants. gx is exact copy of fx when fx gives all order derivative to the fx what it wants, to the gx what it wants. That's it. No other information is required. So actually gx, it fetches the net energy. Like we say that kind of 3D graphic. OpenGL is a game of vertices. Electronics is game of resistance. Okay. Artificial intelligence is game of information or features, whatever information. So like that. So this uh, polynomial approximation, gx approximating fx, is a game of derivative. If fx, if you start giving all the order of derivative, gx can replicate it. Mind it. You may be thinking that I have so many things. Now we will go step by step. Now if fx has full set of polynomial x to the power 1, 2, 3, 4, all, just giving the partial, just giving the derivatives, then gx can replicate fx. But it may not be exact. In a sense, it is x1, x2, x3, then x to the power 6, then x to the power 7. In between it is missing, but it will have everything. So that way it is approximation. One thing. What is missing here? The constant is missing. If I say approximation gx, approximation of fx, if I say any line curve, just think about the line curve. The line curve equation is y minus y0 equal to dy by dx x minus x0, where y equal to y0 plus dy by dx x minus x0. If that is the case, then y0, y0 and x0, these are the 2 points through which line is passing through. So if I say y equal to y0 plus dy by dx x minus x0, where dy by dx is differentiation is where x equal to x0. Now y0 is nothing but function at x0. So y equal to function at x0 plus dy by dx x at x0, then multiplied by in braces x minus x0. If that is the case, then this is the actual equation. So gx, what we have written as polynomial approximation of fx, there I have to add in the beginning fa, fa. So gx is now fa at point x equal to a, fa plus dfx by dx at x equal to a, x minus a divided by factorial of 1 plus d2fx by dx square x minus a whole square divided by factorial of 2 plus d3fx by dx at x equal to a, d3fx by dx cube at x equal to a into x minus a to the power 3 by factorial of 3. Keep doing like this. If you keep doing, if you keep doing like this, then it will come as a kind of a full-fledged polynomial equation gx, that is approximation of fx. Okay, so that is the scenario. Now we will prove through another way. Taylor the way, Sir Taylor, Mr. Taylor, he proved it. So now consider, okay, now consider that fx, okay, so now consider that fx equal to, it is a full-fledged polynomial equation. Fx equal to full-fledged polynomial equation, fa. Here gx is fa, and here also fx equal to fa plus kx plus, or if I just say fa plus x square plus x to the power 3 plus x to the power 4 up to x to the power n, that is fx. Okay, if that is fx, then what is its, I'm sorry, I will insert a. So fx equal to fa plus x minus a plus x minus a whole square plus x minus a to the power 3 plus dot dot plus x minus a to the power n. This is the polynomial, this is the fx where it is passing through a point where x equal to a. Okay. Now if I give first order derivative, if I give first order derivative, if I give 0th order derivative, there is no derivative where x equal to a. In that case, x minus a whole square all becomes 0. Only f a comes into the picture. So gx receives without any derivative at x equal to a as fa. So gx equal to fa, first one. Now first order derivative. First order derivative fa gone. That is now x minus a becomes 1. X minus a becomes 1 and rest becomes 0 because x equal to a. So 1 comes here. If 1 comes here, then first order, then now it becomes fa. The gx equal to fa plus dfx by dx. This is what it is receiving, dfx by dx at x equal to a, x minus a divided by factorial of 1. This is the fundamental the Taylor is also saying, because it is, this is where it is exact replica. We gave the explanation why we are doing like this. Now it is 1 into x to the x minus a divided by 1. So it becomes fa plus x minus a. Now second order derivative. Fa first gone, first derivative only gone. Next is x minus a, second derivative that is also gone. Next is x minus a to the power 2, x minus a to the power 2. Okay. Now this we will derive twice. This we will derive twice. So it will become 2, 2 into 1, 2 into 1. Rest will become 0 because x equal to a, x minus a. So it gives 2 into 1. Now this one would become fa plus x minus a plus 2 into 1, that is d2fx by dx square at x equal to a, 2 into 1 into x minus a whole square, then I have to divide by 2 into 1. So what is dfx, what is d2fx by dx square at x equal to a, whatever it is there, into x minus a whole square divided by factorial of 2. Similarly, if third order derivative I am giving, that will be 3 into 2 into 1. So there now the full phrase it will be fa, gx is fa plus dfx by dx at x equal to a, x minus a, plus divided by factorial of 1 plus d2fx by dx square at x equal to a, x minus a whole square divided by factorial of 2 plus d3fx by dx cube at x equal to a, x to the power x minus a to the power 3 divided by factorial of 3 plus. So if I keep doing like this, then at the end it will become dn fx by dx to the power n into x minus a to the power n divided by factorial of n. So this is gx equal to fa plus dfx by dx at x equal to x minus a by divided by factorial of 1 plus at the end d to the power n fx by dxn x minus a to the power n divided by factorial of n. This full phrase is the polynomial approximation of fx. This is Taylor series. This is Taylor series. Okay. Now, if this is kind of a Taylor series, if this is a kind of a Taylor series, then next comes is maclaurin series. Taylor series, polynomial approximation of any function fx as gx. Maclaurin series. Maclaurin is saying that when x equal to when x equal to a, when x equal to 0. Okay, when x equal to 0. So I have now consider that a equal to 0. So fx approximation at gx we calculated. Now fx was polynomial. Fx was polynomial for which we have gx. Now fx is not only polynomial, it is mixture of every algebraic thing. Still, since dependency is only on the derivative, fx, can you tell me it is polynomial or sinusoidal? I don't care, because fx to gx, the what gx want from fx is only derivative, first order, 0th order, first order, second order, third order at x equal to a. That's it. Then it makes its own polynomial approximation expansion. That is Taylor expansion polynomial approximation. Usage of Taylor polynomial approximation expansion is infinite. I won't say these are the places it can be used. The usage is infinite. So Mr. Taylor has done something which is very, very powerful. Not powerful, very, very powerful. But we also did it. Somehow there was a situation where I also personally needed polynomial approximation. I did it, but later I came to know it is already done by Mr. Taylor. So there is another person now, Mr. Maclaurin. So Mr. Maclaurin, God has gifted even even a special brain to Mr. Maclaurin. So what Mr. Maclaurin, okay, what Mr. Maclaurin is saying, okay, is that can we think x equal to a? At that point, what is the expansion? That is the actual expansion of the many algebraic function. Not required, it is polynomial. So like fx equal to e to the power x. What is polynomial expansion of e to the power x? Not e to the power x minus a. Consider e to the power x. If e to the power x, considering x equal to a equal to 0, actually it is e to the power x minus a. Consider a as 0. So e to the, what is the expansion of e to the power x? Then gx is fa plus dy by dfx by dx at x equal to a, x minus a, plus d 2 fx by dx square x minus a whole square by factorial of 2. Keep doing like this. So f at 0. So e to the power x at 0 is 1, plus dfx by dx at x equal to, where x equal to a. So differentiation is ex only. The differentiation of ex is ex only at x equal to 0. Okay, because a is 0, at x equal to a means a is 0. So that is 1 again. X minus a, x minus 0. So x, 1 plus x plus, now d2 fx by dx square. Double differentiation is also e to the power x only. E to the power x minus a. When a is 0, I mean when x is a, then it is e to the power 0. At that moment it is 1 again. X minus a whole square, that is x square, divided by factorial of 2. If you keep doing, then it will become 1 plus x square by factorial of 2 plus x to the power 3 by factorial of 3 plus x to the power n by factorial of n. This is polynomial expansion of e to the power x. Can you see where I said x equal to a? Okay, and I mean where x equal to a, where a is 0, where a is 0. If that is the case, can someone try sin x, cos x, tan x, and something like that? Ln, natural log x, whatever. Someone can try it. This is called Maclaurin series. Maclaurin series is nothing but a special case of Taylor series where x equal to a, anyway that is a Taylor series where a equal to 0. Let's try sin x. So sin x is first fa sin at 0. So this is 0 plus dfx by dx. So differentiation of sin x is cos x. Cos x at a equal to 0. When cos x at a equal to 0 means 1. 1 into x divided by 1. It starts with x plus d2 fx by dx square. So first differentiation is cos x, then minus sin x. So minus sin x, x equal to 0 is 0. So that is gone. d3 fx by dx to the power 3. First is cos x, then minus sin x, then minus cos x. Then x equal to 0 means minus 1. So minus x to the power 3 by factorial of 3. So it became x minus x to the power 3 divided by factorial of 3. Next will be gone. Again, it will be like this, keep on happening. So this is polynomial expansion approximation of any algebraic function. Logarithmic also someone can try. This is Maclaurin series. So we will see if we can prove it through other way, and then we will see where are the places where the Taylor series is like, you can say, divine. You have divine water or whatever, divine, where you don't have any other alternative. Hint is, can we calculate directional derivative of a function along a vector u? We have derivative of a function along independent component x. Derivative of a function along independent component x-axis. Can the function is fx, can I calculate derivative of function fx along any unit vector u, not necessarily x? If I have xy plane, consider xy plane, there is a x-axis, there is a y-axis, x-axis, y-axis. On this plane, there is another unit vector u, unit vector I, unit vector j. On this plane, there is another unit vector u. If there is another unit vector u, there is another unit vector u, then what is the partial derivative of function fx or directional derivative of function fx along unit vector u? What we are trying to achieve here? If I say directional derivative along or directional derivative along unit vector u means if fxy, rather fxy, function over xy plane, fxy. So if I have function over xy plane, fxy, then if I calculate partial derivative along I vector, means how much function? Okay, this is xy plane. This is xy plane. Okay, if this is xy plane, then this is 3D. Okay, it is very big. So this is xy plane. If this is xy plane, then this is a 3D fxy. Fxy can be a sphere, or it looks like a sphere only, or cylinder, whatever it is. So this is xy plane and this is a sphere. Now this is fxy. Now, if I want to calculate derivative of fxy along x-axis, then it is purely dfxy dx. There is no problem because fxy is in term of x and y1. If I want to calculate derivative along y-axis, then dfxy by dy. What is the derivative of this along any? This is x-axis. This is y-axis, like this. Now, if I draw, this is origin. x-axis, y-axis. Now I draw any line here. Okay, I draw any line here. This is x-axis, this is y-axis, then I draw any line here. What is, if this is the line, if this is fxy, what is dfxy by du? If this is the u vector, u unit vector, this is I, this is I unit vector, this is j unit vector. What is dfxy by dx? What is dfxy by dy? If that is the case, then what is dfxy by du? Directional derivative along u vector. Okay, so what we are trying to achieve here is, if I take u vector, if there is a unit distance change along u vector, then how much fxy changes. If I take a point on u vector u and u1, and there is another point on same line u vector line, if I take a point u1, I take another point u2, then at u1 what is fxy, at u2 what is fxy. So f1 and f2. f2 minus f1 divided by u2 minus u1. That is dfxy by du. Or if I say I have a point u and at a distance delta u there is another point u plus delta u, then f at u plus delta u minus fu divided by delta u. Can someone calculate it? This is directional derivative along any vector u. It is impossible without Mr. Taylor polynomial expansion. So, polynomial approximation. So, that we will see.